Hello, my name is Carlo Fabricatore, and it is my honor and pleasure to be with you today to share some ideas concerning decision making in complex problem scenarios and how game based learning can foster this. I will start this presentation with a few thoughts concerning why debating the topic of decision making in complex problem scenarios is crucial these days. I will then delve into what these complex problem scenarios really are and why they are challenging. I will then discuss how game based learning can be helpful and, in fact, should be architected to foster the ability to tackle complex problem scenarios. I will finally present some conclusive thoughts and perspectives for future work that needs doing. This presentation is focused on decision making in complex problem scenarios. Now, the reason why this is a crucial topic literally surrounds all of us right now, and it has been defining our lives in unprecedented ways for over a year now. So, before delving into formal definitions and technicalities, I would like to invite you to reflect for a few seconds on the COVID-19 pandemic. It all started with a bug, maybe, and then it is a problematic situation indeed that generated all sorts of dire consequences at all levels and all scales. But how are things going? Is it better than a year ago? Worse? By what standard? What are the priorities that should be addressed? Is there a next step crucial to pave the way out of this mess? What did actually cause this mess? Is there a way out at all? And is it really all so bad after all? Is there anything positive emerging out of this tragedy? Is there anything that will perhaps stick with us? Anything that 10 years from now maybe will make us think that perhaps not only we managed to stay afloat and cope, but we actually changed positively. We evolved because the pandemic. Thinking about COVID-19, one may feel that it is really difficult to pinpoint what the problem is, the causes, the effects, and hence what a reliable solution could be. Even more, the COVID-19 pandemic may seem a spaghetti salad of causes and tragic consequences, involving diverse actors at different levels and with no apparent silver bullet solution that can address everything at once. Why is it so difficult to understand what the problem is and what the solution could be? Well, that is because the COVID-19 pandemic epitomizes what wicked problems truly are. COVID-19 is not the first wicked problem that we face, but it is certainly the first one that forced mankind to acknowledge that there are situations that can truly and immediately affect us globally, that can put us on our knees, and which we have to cope with even if we cannot control them, no matter how hard we try. And COVID-19 is also demonstrating how important it is to have the ability to address situations that we cannot fully control. How important it is to be able to take our best shot at it and trying and failing and assessing and changing plans over and over again and again and again, learning through this process so that every iteration means a little step forward, even though that only means damage containment, even though the end goal may seem far away. This is what this presentation is about, this capability, and how games can be architected to foster it. So, what are these wicked problems and why are they so challenging? Well, like I said, COVID is not the first one that we face. And before we delve into why they are challenging, why these wicked problems are really, really nasty, and what is required to tackle them, and how games can help, I would like you to have a very tangible and clear perception of the many looks of the beast. So, what are wicked problems? Well, the COVID-19 pandemic is a wicked problem, just like other pandemics that we experienced in the past. Global terrorism is a wicked problem, and global warming, and global financial crisis, and global deforestation, and racial discrimination, and the list continues. And this is the real challenge that they present. This is what all wicked problems have in common, and which makes them, in fact, wicked. They cannot be definitively solved. They cannot be controlled. They can only be continuously and collectively managed, focusing on the common good. Let's delve into this and let's analyze the nature of the beast. Let us now focus on the challenges that characterize wicked problems. What is required to cope with them? How to befriend their uncontrollability? First and foremost, wicked problems are problems, just not ordinary ones. From a standard problem solving perspective, a problem is defined by an initial undesirable state of affairs that needs to be changed. And this is no different for wicked problems, as they are indeed undesirable conjunctures that most unfortunately compromise individuals, entire societies, and their broader environment. However, the similarity between standard and wicked problems stops here. We can analyze standard problems, identifying a goal state to achieve in order to improve things, and an approach to transition from the current problematic state to the desirable state. Then we can implement the solution, and voila, the problem is solved. Instead, wicked problem situations are ill defined for starters, as start conditions, possible goals, and methods are all to a large extent unclear. Furthermore, they are complex as they are defined by many interacting factors which change over time. Now, this complexity is far more than complicacy, as we will see in detail in the next slide. Altogether, ill definition and complexity defeat standard approaches to analyzing and solving problems. Wicked problems slay problem solving as we traditionally know it, and this is mostly due to their complexity. Now, what exactly is this complexity about, and why is it so challenging to cope with? Well, wicked problems are situations defined by a large number of factors that interact in many ways. This makes wicked problems complicated. Their complexity, however, is far more than sheer complicatedness. The factors that interact change over time, and so does the way these factors interact. And they change in autonomous ways, reacting and reorganizing in order to adapt and eventually resist to external perturbations, which includes, of course, attempts to address the problem situation. Interactions between these factors then generate emergent systemic effects, which cannot be fully understood nor predicted through observing isolated factors and isolated interactions. In this sense, wicked problems are a clear example of how the whole can be greater than the sum of its parts, as Aristotle suggested long ago. Complicatedness, adaptive change, and emergence altogether define the complexity of wicked problems and make them non fully knowable, uncertain, unpredictable, and therefore uncontrollable. To worsen things, wicked problems are never alone. Where you find one, there are usually many other wicked problems around, and they all interact. And they involve multiple stakeholders with conflicting interests, usually, all of which makes it even harder to find solutions beneficial for all the involved parties. In sum, in a world of wicked problems, when it rains, it pours, and it usually rains. Then how should wicked problems be tackled? Well, they can only be managed, not controlled. And this should be done through an adaptive problem management approach that iteratively integrates phases of exploration and evaluation of circumstances in order to formulate assumptions concerning how the world works and what is right to do, planning in order to set goals to pursue and strategies and techniques to pursue them, of course, all based on previous assumptions, and action, which entails the execution of an established plan, as well as a continuous monitoring of the environment, looking for signals suggesting that something may need to be reconsidered. Now, this process clearly relies on continuous meaning making to interpret the scenario at hand and revise plans and underlying assumptions accordingly. This is a very challenging process, as it requires foregoing the illusion of control. There is no sticking to the plan, as everything has to be defined and revised iteratively. It requires accepting that one can never figure it out, as this process should be driven by continuous meaning making. And the process is challenging because it requires learning and unlearning continuously and iteratively in order to adapt plans and assumptions to changing circumstances. Now, this is an interesting challenge because it entails high performance decision making skills, involving the ability to infer patterns, implications, and act based upon learned patterns. In a nutshell, this means being able to act, making assumptions, and forecasting the future, all based on highly incomplete and uncertain information, which is something that very few manage to do efficiently. This challenge is also interesting because many people do adapt plans. They are quite capable of doing that, but not assumptions. And this is because revising and adapting assumptions requires acknowledging and questioning one's own beliefs, which is psychologically taxing. Then add to the mix that all this should be a collective process, and you can grasp quite well how challenging coping with wicked problems can be. Now, this begs the question, how can this adaptive problem management capability be learned? Well, if properly designed, games can be an answer to this question. Let us start now delving into game design and how games can be leveraged to promote adaptive problem management. To start off with, it is important to identify key qualities required by APM in order to then discuss how this can be fostered through games. Then, what is needed? What should players learn in order to improve their APM capabilities? Well, tons of things, to be honest. However, there are some pivotal ones which I will focus on in this presentation, and which are comprised in what I define the APM mental toolbox. First off, let me briefly focus on who should develop APM capabilities. So, who needs APM? Well, the short answer is everybody. In fact, the sooner people start learning how to engage in and cope with complex problem scenarios, wicked problem scenarios, well, the sooner the better. In particular, APM is crucial for strategists who operate as harmonizers in critical situations, meaning that their purpose is to facilitate equilibrium and positive transformation in wicked problem scenarios, and their role requires identifying and pursuing the common good, formulating and adapting win-win strategies accordingly. And what does the APM mental toolbox entail? Adaptive problem management requires striving for the common good, which entails the ability to explore critical situations in order to identify the best possible solutions to satisfy multiple and potentially conflicting needs and interests. In addition, APM requires coping with complexity, identifying strategies to pursue the best possible outcomes, and adapting these as needed. All this in turn requires crucial capabilities and attitudes, including interpreting the environment through a system of systems perspective, analyzing the environment as a network of nested and interconnected systems comprising interacting elements and environmental conditions in which what happens in one system may affect others, and causes and effects are not fully discernible. Then there is quick guesswork, consisting in the ability to swiftly determine what could likely be helpful to do and how things probably function. There is confidence in the fact that meaningful action can indeed lead to the common good. And there is adaptability, intended as the ability to continuously pay attention to signals which may suggest that something should be changed, and readiness to change both decisions and worldviews. It is worth noting that quick guessworking is actually a rather challenging thing to do, as it entails the ability to quickly analyze and synthesize available information and anticipate the future based on it. This in turn entails the integration of deductive top-down reasoning, which is the ability to infer reliable conclusions from reliable premises, inductive bottom-up reasoning, which is the ability to formulate reliable generalizations from circumstantial observations, and abductive take your best shot reasoning, consisting in the ability to draw the simplest and most likely valid conclusion from uncertain or incomplete information. Then how can games help? How should they be designed to foster the APM mental toolbox? Given the importance of integrative learning, iterative collective activity, meaning making, and complexity conditions, in order to promote the APM mental toolbox, games should fulfill 4 key requirements. Number 1, they should elicit gameplay tasks that are collective, feedback-driven, iterative, and adaptive. Number 2, they should promote motivation, fostering sense of need and agency towards simulated scenarios, as well as real-world situations that are reflected by the simulated scenarios. Number 3, games should foster integrative learning, knowledge plus skill set plus attitudes, through collective activity and meaning making. And number 4, games should simulate and modulate complex systems, mirroring wicked problem scenarios, reproducing change, uncertainty, unknowability, unpredictability, and uncontrollability that characterize wicked problems. This should be done. What should be done is implementing complexity, but not too much complexity, in order to promote learning without actually compromising it. The nature of adaptive problem management makes it paramount to promote and orient meaning-making processes through game design. Then, what exactly is the role of meaning-making in the gameplay activity, and how can this be influenced? The Russian theory of activity, also known as activity theory, represents a reliable source to address these questions and design games accordingly. Activity theory is a multidisciplinary framework of theories and research developed since the 1930s. The activity theory framework supports multidisciplinary approaches for the study of contextualized human activity and for the design of systems promoting desirable activity and the general well-being of the involved people. This framework conceptualizes human activity as an iterative, goal-oriented process which integrates mental and practical components, is mediated by people and artifacts, and is driven by continuous meaning-making. According to activity theory, people like Panchito here interact with the external world based on what they can sense from it. In Panchito's case, some sensations will slip away unattended, but others will draw his attention. These sensations will be interpreted by Panchito through meaning-making, leading to the formation and update of mental representations. Such meaning-making process is the product of interplaying cognition and affection. In other words, mental representations reflect what we rationally think of the world as much as how we feel about it. Among other things, these mental representations will reflect what Panchito thinks and feels about why acting, what to do, how, when, and where. Hence, they will ultimately define Panchito's motivation to act as well as his action plan. Activity theory stresses that the motives driving Panchito's action will reflect what he finds subjectively meaningful, what's important to him, as well as what his surrounding sociocultural setting deems significant. For example, what society considers as acceptable, important, etc. Panchito's mental representations will then drive his interactions with the external world, as he will interact with other objects and people to achieve set goals based on his plans and based on his knowledge of existing norms. Through meaning making, Panchito will continuously develop knowledge representations, attitudes, and skill sets, all of which will be reflected in some of his mental representations. Furthermore, Panchito will hone his operational skill set through practical activity. Now, three important things should be highlighted from this process. Firstly, decision making is an aspect of meaning making. Secondly, learning is effectively meaning making. And thirdly, decision making and meaning making depend on information flowing from the activity environment to Panchito, and the attention that Panchito puts on such information flows. It can be concluded from this that if we wanted to orient Panchito's decision making and his learning, we should influence his meaning making processes. To this end, we should make relevant information readily available to Panchito in his activity context and draw Panchito's attention to it. Furthermore, activity theory suggests that there are key types of knowledge that people seek as a matter of priority while construing meaning through activity. Number one, how things function, how they can be operated, and with what effects. Number two, how things interact, why, and with what effects. Number three, how people interact and with what effects. Number four, how people are affiliated or associated, why and with what effects. And number five, what is deemed good or bad, acceptable or unacceptable by a community of interest. We can conclude from this that these types of information are more likely to quickly affect meaning making, if they are available, of course. Now, why is all this important? Well, simply put, because it holds the key to influencing meaning making and therefore learning in games. Well, first of all that I have discussed so far holds true for any type of activity, including the gameplay activity. In fact, conceptualizing a game based on this model is quite straightforward. Panchito is the player, of course. The context is the design game space that Panchito has to deal with. And Panchito deals with such context through interacting with objects and other actors, including other players, in the pursuit of meaningful game goals and based on systems of rules, gameplay schemas. Then, in terms of game design, activity theory implies that there are three powerful elements that can be used to influence meaning making by design. Information flows that the game conveys to the player to reveal key aspects of the game state. The gameplay system involving objects, entities, and rule systems that ultimately define what can happen in the game and what can be done by players. And gameplay settings, which set physical, sociocultural, and historical conditions that define and justify how, when, where, and why things happen in the game. Altogether, these elements can be systematically architected to convey meanings to players based on a very simple procedure. And by doing this, what happens is that meaning making can be influenced, but also ill definition can be generated. So the procedure to leverage these elements is as follows. First, it's important to identify the mental representations that should be promoted and map these representations to key meaning-making information that could affect it. Secondly, the key meaning-making information should be contextualized through the design of the physical and or the socio-cultural historical setting of the game. Then, it's important to identify elements of the gameplay system that could convey this information and design gameplay situations and events suitable to convey the desired information flows. Finally, it's important to implement complementary information flows with queuing function in order to focus the player on the relevant meaning-making information as needed at the right time. Finally, by hiding and revealing aspects of the game space, information flows can indeed be leveraged to define and modulate unknowability and uncertainty throughout the gaming experience. Hiding and revealing information about the game state is a good way of generating unknowability and uncertainty. However, it is not sufficient to generate the degree of complexity that elicits adaptive problem management. Then, how do we simulate more complexity, and how do we make it just enough complexity? What design features should be implemented to pump up complexity without making it explode? In order to foster adaptive problem management, a gameplay system should be architected ensuring that players engage in scenarios that are certainly complicated, more often than not complex, but never too complex. This entails implementing and modulating change, unknowability, and unpredictability in order to ultimately generate emergent phenomena, ill definition, and uncontrollability. All these conditions are essential to elicit and foster adaptive problem management capabilities. All these conditions can be implemented and modulated through three key design features: topology and mechanics of the game space, event generation and propagation, and patterning of the game system. Let us now explore what these features consist in and how they can be tackled by design, starting with the game space. Talking about complex games might lead people to intuitively think about big games with plentiful different things happening. This is somewhat correct. However, what should be the origins of complexity might not be that intuitive. In fact, the path to complexity starts with simplicity, believe it or not. Overall, complex systems are complicated because they are composed of many elements that interact in many ways. Plus, they are dynamic because their elements interact ongoingly. In spite of this, complex systems are not chaotic. Albeit they are not static, complex systems exist in dynamic equilibrium, meaning that things in a complex system change based on routines. That is, until some major perturbation happens, in which case the system reacts and changes its organization in order to respond to such perturbation. A simple but relevant example of this phenomenon is represented by some schooling fish species. Under normal conditions, they go about their ordinary life cycle routines, keeping their school dynamic but not chaotic. Then, when a predator approaches, they reorganize into shapes that mimic huge fish in order to fool the predator and scare it away. Interestingly enough, what makes real complex systems complex and yet somewhat manageable is the fact that the complexity of their structures and behaviors actually originates from simplicity. Complex systems are characterized by hierarchical global structures that result from composition of simple substructures. By the same token, the global behavior of a complex system is the result of simple interactions between neighboring subsystems. The behavior of each subsystem is the result of simple interactions between neighboring entities within it, and so on and so forth. This is effectively what defines complex systems as proper systems of systems, and determines to a large extent their ability to adapt and evolve. In particular, their structures result predominantly from the combination of two key topologies, centralized and distributed. The former is more stable, as one element somehow controls the others, but for the same reason it is also more fragile. The latter is, well, the opposite, more flexible and able to evolve, but also less stable. Together they grant to a complex system a good balance of stability and flexibility. The systems of systems perspective allows analyzing complex systems incrementally, adopting a black box mentality. In order to interact with the system, the starting point is understanding how it will react as a whole to external input. No need to understand what it is exactly composed of or how its parts interact. If need be, one can then open the black box, look into it, and deal with the tinier black boxes that it contains, and so on and so forth. Now, in terms of games, subsystems can be seen as clusters of actors, objects, and environmental conditions that interact based on design gameplay schemas. For example, a city dwelled by non-player characters. By design, these clusters may have specific needs, for example, food to feed the NPCs, and functions. For example, the city can be an important fluvial harbor, and they can interact with external subsystems, reorganizing if need be. For example, in case of a ground attack, the city gates will be closed, citizens will barricade in their houses, and soldiers will organize and fight from the city walls to repel the attackers. Complexity can then be implemented in a game system by mimicking the hierarchical topology of a complex system, meaning that the game space should be structured as a system of systems. Furthermore, game elements should be involved in multiple interactions and connections. However, this should involve mostly neighboring elements and should be regulated by simple rules. In particular, 4 key types of gameplay schemas should be defined to organize the gameplay system. Structural schemas, to govern the physical organization of parts in a whole. Causal mechanistic schemas, to regulate material interactions among entities. Social schemas, to regulate social associations and interactions based on sociocultural and historical settings underpinning the game. And workflow schemas, to regulate the sequencing of player tasks and activities from other entities. Knowledge of these schemas will be the most important learning outcome engendered by the gameplay activity. Hence, they should reflect whatever aspect of the real world players should learn. To abide by our complex but not too complex mantra, complexity can be modulated by accounting for simple factors that define the topology of the game space, including the number of clusters within a system, the number of elements within a cluster, and the number of connections between elements of a cluster and between clusters. So far, I've discussed structure and dynamics of complex systems, stressing the importance of compounding simplicity to simulate complexity in games. However, this is not enough to simulate the type of complexity required to promote adaptive problem management. Systemic change is the issue to tackle, and systemic change in complex systems means more than the immediate effects of interactions between entities. Systemic change in complex systems is the result of events that propagate across time and space with growing effects. The components of a complex system tend to interact locally with their neighbors. However, this doesn't mean that the effects of their interactions remain local. On the contrary, dependencies in a system make it so that effect propagates at large scales. This means that a small and circumscribed interaction happening in a specific place at a specific point in time can later on generate way larger consequences in remote areas, within or even outside that system. This is epitomized by the metaphorical example of the butterfly effect. Due to dependencies between systems and propagation of effects, a butterfly flapping its wings could theoretically affect the formation of a tornado in a very remote place. In fact, in the world of complex systems, small changes here can indeed generate huge changes there. Now, event propagation is a key feature that allows complex systems to interact with external elements, adapting and evolving as needed. It is a pivotal aspect of wicked problem scenarios, and it should therefore be mimicked in games aimed at fostering adaptive problem management. Luckily, complex change can be mimicked by leveraging simple mechanism of hierarchical event generation and propagation, non-player triggered events preferably. First off, by event, I refer to the effects of an interaction between elements of a game system. Therefore, an event is a game state change that affects entities, environmental conditions, relationships, and interactions, in isolation or clustered. Events will obviously be generated by some interaction, which will affect the involved elements and or, due to propagation of effects, it will impact other elements. Event propagation is hierarchical and can be modeled as a combination of radial and cascading patterns. It all starts with a source cluster within which some key interaction happens. Such interaction can generate a state change within that cluster, which is the simplest possible event. The same interaction can also generate effects that propagate radially, affecting other neighbors' clusters. Besides, that interaction can also affect more remote clusters, albeit indirectly, through cascading propagation of events. For example, this hierarchy could represent a situation whereby the source is a fertilizer factory and the initial incident is a fire in the factory. The fire could cause a factory to burn down completely. In turn, this could leave people unemployed and cause a shortage of fertilizer in town, and a dip in the stock market, and pollution in a river, and maybe the explosion of a nearby deposit. Now, the explosion, in turn, could set a nearby slum on fire, which could hurt lots of people and cause a hospital crisis. Note that this propagation hierarchy has different areas of impact and involve effects that happen at different times and have different magnitudes. Overall, this hierarchy generates global effects as events propagate across time and space. And this is precisely what should be simulated in order to train players to act locally and think globally. It's all about the butterfly effect. Now, event generation and propagation can be modulated leveraging simple heuristics. It all boils down to simulating the butterfly effect and modulating difficulty. Concerning the butterfly effect, event propagation hierarchies should be architected ensuring to involve interactions with clusters highly sensitive to small changes and propagating, 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 and propagating. However, complexity should also be controlled. Concerning event generation and propagation, gameplay activities should be designed to incrementally engage and support players in a multifaceted challenge. Firstly, players should realize that some events occurred and were interrelated, leading to awareness of propagation hierarchies. Secondly, players should understand what has caused what, which translates into comprehension of propagation hierarchies. Thirdly, players should understand how effects can be altered, which strengthens comprehension of propagation hierarchies, and it also promotes the ability to anticipate events. Lastly, players should understand how to promote or prevent events. This also translates into enhanced comprehension of propagation hierarchies and ability to anticipate events. Reversibility of events is also a good heuristic that can be leveraged to modulate difficulty. Finally, branching of radial propagations and length of cascading chains should be increased gradually, as well as the propagation time, which is how long it takes for a propagated effect to emerge from the moment when the originating incident was triggered. Composing simplicity in order to create complex structures and dynamics is fundamental to simulate wicked problem scenarios. However, the scale of these structures and the articulation of their dynamics can still become overwhelming, even if they come from composition of simple elements, unless structures and dynamics present some degree of repetitiveness. An interesting thing about complex systems is that they self-organize based on patterns. This means that they present a degree of repetitiveness in how elements are structured and interact within a system, and how the whole system interacts with whatever lies outside its boundaries. Weaving is a good example to understand how patterns can engender highly elaborated systems. In fact, the very same word complexity derives from the Latin word complexus, which means interwoven. Imagine that. Now, think of threads as components of a system. These are connected through weaving them, thus forming a fabric. Fabric can be simple, such as the one displayed here, or rather complicated, as in the case of this rug. However, as elaborated as this rug may seem, it is in fact composed of simple patterns, sapiently combined. Now, patterns allow complex systems to behave and evolve in non-chaotic ways. At the same time, patterns facilitate comprehension, anticipation, and analogical reasoning, thus making complex systems easier to analyze and even predictable to some extent, which is a good thing. Patterning a game system can therefore be a very effective strategy not only to simulate real-world complexity, but to actually facilitate its management. Game systems can be patterned, focusing on 4 key types of patterns that define how things are usually organized. Structural patterns, representing models of physical organization of parts in a whole. For example, a stereotypical structure of a town, with key types of buildings and a core layout, including perhaps a hardware store. Then you have causal mechanistic patterns, which model cause-effect material interactions between game entities. For example, concerning a hardware store in town, core schemas defining what kind of tools are commonly available in hardware stores, and what these tools can be used for, and how they can be acquired. Then there are social patterns, which model social associations and interactions within the game, based on some sociocultural and historical background. For example, the social setting commonly found in a hardware store and schemas defining which social interactions will likely be acceptable in most hardware stores. Then there are workflow patterns that represent stereotypical sequencing of tasks. For example, daily routines defining opening and closing times and therefore conditioning when one should likely be able to go to a hardware store. Now, the patterning of systems can then be modulated by applying some simple but important heuristics. Firstly, the frequency, scope, and location of repetitions should be harnessed to create large compositions of a limited variety of small patterns. All this in order to create something that is complex but is manageable at the same time. Then implementing the same patterns in different contexts can be useful to foster inductive and deductive thinking, and consequently help players to forecast the future, anticipating what might come next. By extension, absence of a pattern in a condition in which it would have been expected can promote abductive thinking, leading players to formulate likely explanations as to why what was expected was in fact absent. And we've finally come to the end of our little exploration of core topics concerning adaptive problem management and the implementation and modulation of complexity in games. Now for some conclusive thoughts. What I've presented today is only part of a much larger design framework that we're developing with my co-researchers. In spite of the importance of wicked problems and the potentialities that games offer to foster adaptive problem management, there are a few products that overtly address this challenge, and there is little research, relatively little research, on this subject. Therefore, I would really like to first and foremost invite you to join forces. There is a lot of work to do, really. In particular, formal education is an obvious front to promote adaptive problem management, both in schools and corporate environments. However, we're actually working on informal education as well, focusing on intergenerational learning and lifelong learning. I also believe that it is important to identify wicked problems and opportunities to design and use games to tackle them, not just to learn about them. For example, in the EU, we are working on projects in the context of mental health care and social isolation and penitentiary systems. Whereas in the US, we're working on equality, inclusivity, and racial discrimination. And last but not least, we're also developing formal instruments for the evaluation and design of games and the assessment of complex problem management capabilities. With this, I conclude my presentation. I thank you very much for your attention, and please do get in touch. There is really much work to do on this front and much urgency as well. Thanks again, bye bye, and be well.